So thank you for being present here. So the numbers have been decreasing, over the past summer sessions, but yeah, but glad that you could turn up. So today I'll be speaking about how to do fixed point arithmetic in somewhat homomorphic encryption schemes. So many terms they might be new to many of you. So I'll go through the very basics and then I will. I'll tell you. So I'll start from basics, very basics. Okay. So before that, so privacy. We are all in the digital age. We are so worried about privacy, right? So Cambridge Dictionary, defines privacy as the state of being alone, or the right to keep one's personal parameters and relationships secret. Okay. So, and of course, we appreciate the need for privacy in the digital age, right? I think one of the main reasons for this, the increased concern in the privacy, of our data is because of the, due to the ease of copying, transmitting and processing our data in the electronic medium. Of course, privacy has been concerned right from time immemorial, right? But then the way we used to store information, say on a leaf or on a metal or metal sheets or whatever. So the physical form itself kind of helped in providing information secrecy or privacy. Okay. For example, even our banknotes, they provide kind of information security, right? So it's just that it's not that because of the physical features. For example, the type of ink used, it's not easy to replicate that. Okay. So it also provides kind of information. Okay, you can call it information security, not necessarily the privacy, but because in the electronic age, the ease of manipulation and transmission of information is so easy that the need for privacy has has increased, and people talk about it all the time. So I just to give you an example of privacy in healthcare data, just arbitrarily chosen example. So in recent years, healthcare data breach, they have increased in the frequency. For example, the largest database on an insurance company, though it gave away like information about 80 million people. That many people they were impacted. So when I searched for healthcare data breach, this was already a couple of months ago. So it was already 66,000 hits. So that means that there are so many breaches happening, and there's so much talk about data breach. So clearly we see that people are worried about the privacy of their personal data. So, and of course, if we take the same example of medical data, so we need medical data to do some analysis, right? For example, it will definitely any analytics on that medical data will in turn improve the health service. Okay, so we need the data of the patients, okay, so that we can improve their health service. But yet we should keep we should kind of maintain the privacy. Okay, so these are two conflicting goals. Okay, so for example, just to take an example in genome sequencing, for example, so what are called MAF, minor allele frequency, I cannot even pronounce it, sorry, allele, I guess, frequencies, and having distance, edit distance, so there are many statistical tests that we can do, okay, and this all tests will help in genome sequencing, okay, and of course genome sequencing has a lot of implications in improving the health service, right? So you can predict the diseases in advance, and okay, I'm not an expert on that, just to give you an example. Okay, so of course there are many other settings where we are concerned about the privacy of our data. For example, okay, in email and social network databases, Facebook, now and then it will be in news, right, about users' privacy, how they are misusing the data, like, and so on. Okay, so, and e-auctions, for example, how to determine the highest bidder, okay, in such a way that you don't leak the information about the individual bits, yet you want to arrive at the highest bit. Okay. So for example, probably I should have told in the beginning that what I am talking about is joint work with my former colleagues from Bristol. So this work was part of my postdoctoral research. So I've continued to work on this topic. So with Shyam, I'm working on homomorphic encryptions, but what was still a work that is still a work in progress. So that's why I chose to present the work that has already been published. Okay, so during my postdoc thing, I was part of a European Union funded project called Homomorphic Encryption Applications and Technology. So we considered the following projects. So where we want to, where of course we want data to do some processing. Okay, yet we were worried about the privacy of the data. For example, in the smart electricity grids, so in smart electricity meters, we want the usage information, right? So that we can better supply, you can maintain a balance between demand and supply, okay? And then, for example, in automated crime detection, so suppose we have countries like you want to, police are on a hunt on a criminal, and they have got some leads, and they want to search the databases of the citizens of their country so that they can do a match. So how they can collaborate? Okay, the two countries can collaborate so that the law enforcement agencies can get to know whatever the information they want. Yet but yet that the privacy of the citizens is maintained. So they basically get what they want and nothing more than that. Okay. So these are some scenarios where, and of course in satellite data analysis, we will talk about this case study in more detail later in the talk. So here, for example, the satellite owners and the ground station, of course, they are all maintained by different parties. Okay, so because you are using a shared infrastructure, so again the privacy, that concern about privacy will arise. Okay, so we'll get into the more details later on. So as I mentioned previously, privacy and outsource analytics, they are contradictory requirements. Okay, so the question is, can we use encryption to achieve privacy, yet we are able to perform analytics on that? Okay, so, and the problem is, so just to remind you, what is an encryption scheme? It takes a message and a key, and it produces an output ciphertext. Okay. Okay. Like I say, for example, in the case of healthcare, I mentioned we need to do genome sequencing, right? For that, we need patients' data. Okay. Okay. But the point here is, we should use only that amount of data that is necessary for our computation. Okay. But usually when you just, if you are given the database as it is, all the patient's name, their whatever age and all their medical history, right? But that should not happen. So if you're given data, the whole data, then of course you can do analytics, right? But the point is, we want to give out data in such a way that we will only be able to extract information so that, whatever you want to compute. For example, suppose you want to compute Hamming distance between two DNAs, you should only be able to get the result, nothing more than that. So this is the the problem we are trying to address. So the point is, can we use encryption technology to do all these things? Okay, but what is the basic problem? Okay, for that, what is an encryption scheme? So basically, it takes a message, a plain text, and it produces what is called a ciphertext. Okay, so if you just look at the ciphertext, it's gibberish. Means you should not, without if you don't have any knowledge about the secret key, you should not be able to infer anything about the underlying data. Okay, so this, of course, there's no question on computing on ciphertext. Okay, that does not arise. Okay, so here, so we use a special type of encryption scheme called homomorphic encryption. Homomorphic encryption schemes. Homomorphism is a notion from math and algebra. So where that means that, for example, in algebra, what it means is, suppose you have a map between two sets, a function. So if you do operation on this, say an addition, and take the map, it is nothing but taking the individual maps and then performing the addition. So just in cryptography we have just borrowed the term homomorphic, that term. So in homomorphic encryption, basically if you add two ciphertexts, so then you will get an encryption of the sum of the messages. And if you multiply two ciphertexts, then you get a product of the encryption of the product of the ciphertext. Okay. So how can we use this tool to achieve to achieve privacy and as well as outsource analytics is, you encrypt your data, all your medical data, and send it to the party who wants to do analytics, and he will be able to still operate on the encrypted data and produce an encryption of the result, whatever, and give it back to you. And you can because I have the secret key or you have the secret key, so you can decrypt and then give me back the result. Okay. So is it clear, or should I go over again?
Another basic question. So the encryption scheme is homomorphic but not necessarily isomorphic. That means there is some kind of an information loss.
Oh, of course. No. There is. Oh, yeah. Oh, okay. Yeah. So literally, we cannot take this, the difference. So there's nothing called isomorphic encryption scheme. It's just the name we have borrowed. It's just a name we have borrowed. So of course, there is no loss of data. There is absolutely. If you have the secret key, you will be able to, get back the. Yes. So probably, I think for the benefit, I'll quickly repeat. So you have some personal information, okay, you want to outsource, for example, your medical history, or your or a hospital, you have information about all the patients, okay. You encrypt using you give me all those information not in the plain text form, in the encrypted form, okay. Because I don't have the secret key, okay, I will not be able to get to know what is the information about the patients, okay. I will not able to get anything, but I am still interested in doing some processing on it. So I will be able to, so there are encryption schemes called homomorphic encryption schemes that allows me to do whatever operation I want. At the end of it, I will get encryption of the result I want to know. Because I don't have the secret key, I will not be able to decrypt. I will send it to you because you are the owner of the data and you know the secret key, right? So you will decrypt and you send me back the function result. Okay. So in that way, I will get to know what I want to, the actual value, but I will not know any other information about the patient's records or your information. Okay. So this is the idea.
So the question I have, if you do your operation in the plain text format,
okay.
will it be exactly equal if you do in the encryption?
Exactly, of course, there is no, you will get back your result, okay? There is absolutely no loss of data.
You cannot do it, that's why you are sending for others.
Yeah, of course, because you may not be interested. I am interested in knowing, for my research purpose, I want to do analytics on it, okay? Or it can even happen, for example, okay, so I'll present another scenario. For example, I claim that I come up with a very clever stock prediction algorithm, okay? So, and of course, you are a client and you have a company and you want to predict the stock prices, and of course, in the obvious way is, I could give out my algorithm to you, okay, or you can give me all the data about the whatever company so that I can make the prediction, okay. But this way, then if I'm making business out of this, product, then I am not willing to give you, nor you will be able to give me all the information. So what you do is you give that information in an encrypted form. I'll do the analytics, okay, and you will get back your result in the encrypted form. So I will not know the value of the stock price in the future, like in the foreseeable future, and yet I will not give you the, my algorithm, okay. So both are happy.
So I know current on these homomorphic encryption schemes like cover a whole range of algebra, right?
Yes.
Computations and
Yes.
so on. Yeah, can you do any arbitrary Turing computation?
Any polynomial time computable function you can do it. And in fact, you can do computation in such a way that you will not know about what the function was applied other than the output result. Anything polynomial time,
But
Yes.
So that's the correct description.
Yeah. Polynomial time. Of course, I mean, we cannot do any operation other than, beyond polynomial time, right? In a reasonable amount of time. Okay. But this is all in theory, So it sounds so promising, right? But in practice, it's about million times slower than, doing it on plain text data. It's million times slower. So, yeah, now let me come to that. So as I said, you can do arbitrary functions, means it's polynomial time computable. Okay? Of course, you can even do even hard functions, but it's going to take longer time. Okay, even complex functions. So this picture will illustrate, So basically, you need to just support two operations, addition and multiplication, because you know that any circuit, any any program you can write it as a Boolean circuit, right? So basically, XOR is nothing but addition over a field of two elements, okay? And then AND is nothing but multiplication over field of two elements. The moment you can do, so I just need to show that you can construct a scheme and claim that you can do addition and multiplication. In principle, you can do anything, okay? So there are already, so the notion of homomorphism on ciphertext, okay, it dates back to right from the beginning of public key encryption scheme. Probably you might have heard about the Rsa encryption scheme, right, which is very popular. So there it supports multiplication of ciphertext. For example, how the ciphertext is encrypted is you take the ciphertext, you raise it to the power of this the public key modulo some number, means you need to take the remainder upon division by some number which is product of two primes. Okay, that's not important. And if you multiply two ciphertext, you will get the encryption of the underlying messages. So RSA is multiplicatively homomorphic, but then you cannot do addition with that. And there are other schemes that supports addition. For example, the PIA encryption scheme. It's a very well-known encryption scheme. So that allows addition of ciphertext, but not multiplication. With addition, you can already even with multiplication alone or addition alone, you can already realize many functions. For example, voting. In e-voting, additively homomorphic encryption schemes you can already use. You just encrypt your vote. Okay, 0 or 1. You vote or you agree. Whatever. No. Yeah, for example, okay, assume there are only two candidates. So 0 and 1, you want to vote for 0 or 1. So you just need to encrypt 0 or 1 and add it up, right? And you will, finally the tally will give you the encryption of the count, okay? So you can simply, so that way you can, already use additively homomorphic encryption scheme for e-auction, so e-voting, sorry. And there were already some, proposals that supports, yes?
Addition supported, can it imply that subtraction is also possible?
Yeah. Again, how you are representing your computation as you need to represent it as a circuit. So you use a Boolean thing, right?
Yeah. So with binary, you have a 2's complement representation of negative.
Ah,
So
2's complement.
You can do multiplication actually because you represent negative numbers as 2's complement of the positive.
Yeah. But again, but then we already know that if you want to do the addition, the integer addition, it's already a nonlinear circuit. You cannot just use XORs, right? Because it's not a F2 linear operation, So that's why you need both XOR and AND. Yeah.
So addition does not imply subtraction.
Yes. So if you want to represent your computation as an arithmetic circuit over a field, so your gates are addition over the field and then multiplication over the field. So this is possible. So when the field is field of two elements, then we get back the Boolean circuits. So we need both addition and multiplication. So in the plain text, we are so used to the operation that we think that we don't need it, but ultimately we are, we still will be needing that. And there were some proposals that supports like any number of additions, but only one or two multiplications. Already many applications are feasible with this, but then still most of the applications are out of reach. Okay, so designing an encryption scheme that supports unlimited or polynomially bounded number of many additions or multiplications on ciphertext remained an open problem until this man Craig Gentry, he designed a scheme. So it was a result of his thesis from Stanford. So his supervisor Dan Boneh was already a well-known cryptographer. So then he came up with this fully homomorphic encryption scheme. That was in 2009. So that was really a breakthrough. So let me more formally explain what do you mean by fully homomorphic encryption scheme. So usually any encryption schemes, for that you should tell how the key is generated. So they all consist of algorithms that you should tell how the the key is generated. Means you need to produce that algorithm should output the secret key, the public key, and okay, in homomorphic encryption scheme, an evaluation key. Okay. So using that evaluation key, you evaluate on the ciphertext. That is expected to be public. Okay. Of course, secret key cannot be public. The public key, as the name says, it's public. Okay. And then encryption, it will take a public key and a message. I'm talking about public key encryption here. So the public key is publicly known, and upon encryption of the message, it will output what is called a ciphertext. Okay. And decryption, it will take the ciphertext and it should take the private secret key, and then it will output the plain text. So key generation, encryption, decryption, it's common to all the encryption scheme. But in the case of homomorphic encryption scheme, we additionally have a procedure called evaluate. So it will take the ciphertext as input and your function represented as a circuit, as an arithmetic circuit or some field. Okay, and evaluation key, which is publicly known. Okay, and it produces it will produce the encryption of the F of the underlying the messages. Suppose C1 encrypts M1, C2 encrypts M2, Cn encrypts Mn. So you will get the encryption of F applied on M1, M2, M3, so on up to Mn. And of course, some desired properties are correctness. Means once you encrypt using a public key, do some operations, and then decrypt using the corresponding secret key, you should get back the message, right? You should get the intended function, right, applied on the messages. Sorry. So evaluation of the ciphertext. Okay. So evaluation, F is any function you want to evaluate on the ciphertext. So that you represent it using an arithmetic circuit. Okay. So the most simple example is F can be addition or multiplication. And then you can add two ciphertext, multiply it to ciphertext. Or if F is a circuit, you can do all the operations. So, and then there is another property called compactness. Namely, if you do many operations, the size of the ciphertext should not grow. Because beyond, before achieving this fully homomorphic encryption scheme, the partially homomorphic encryption schemes, they said, as I mentioned before, they allow one or two multiplications, right? But the moment you start doing more multiplication, even the size of the ciphertext grows. So this is not something desirable.
So one more question.
Yes.
So if let's say I have a encryption scheme that is homomorphic for addition,
Okay.
but not multiplication.
Yes.
And one more that's homomorphic for multiplication. Can I use two separate encryption schemes in the same circuit?
No, currently no. I think if someone does that's really a breakthrough.
So you can
Yes.
merge us.
Yes. Yeah. Yeah, they rely on very different.
You have to invent the right encryption scheme that can support all the.
Exactly. Yeah. So yeah, because they have very different structures, and without access to security, you cannot do anything. So that's the problem. Yeah. And yeah, compactness, the size of the ciphertext should not grow depending on the the operations what you do. And circuit privacy, this is optional. As I said, once you do operations on the ciphertext, preferably it should not even reveal what function was actually evaluated. So this will achieve what is called circuit privacy, or you can also call function privacy. Okay, so these are the properties. Is it clear? Yeah. So usually how these homomorphic encryption schemes are constructed is they construct what is called a somewhat homomorphic encryption scheme that only supports circuits of limited multiplicative depth. Addition is actually easy. The multiplication is always where the problem arises. So first they construct a scheme where you can only evaluate those functions f that have certain multiplicative depth. Okay, and then they magically convert that somewhat homomorphic encryption scheme into a fully homomorphic encryption scheme. Okay, so I will not get into the details. So basically, this bootstrapping is a very expensive procedure. So what really happens is homomorphically decrypting the circuit. For example, suppose you take a ciphertext, encrypt, and you do the decryption, you get the original message, right? But here in bootstrapping, they are homomorphically evaluating the decryption circuit. Okay, so probably I think I should write it down. Okay, suppose you have a message and it became a ciphertext C upon encryption. Okay, and then so once the ciphertext upon decryption you will get back the message. Agreed? So in bootstrapping, so you take a ciphertext that encrypts the message M and you homomorphically evaluate the decryption circuit. Okay. So what are you expected to get? If you decrypt, you will get the message. But the moment you homomorphically decrypt the message, you should get an encryption of the message, right? Another encryption of the message, right? That encrypts the same message. And that you decrypt, you get back the message. This upon decryption, you will get back the message. Remember, in a homomorphic encryption scheme, you apply a function on the ciphertext and you get encryption of the function applied to the underlying message, right? So what is the function when you homomorphically decrypt? So this is like called be homomorphic decryption. You should get, encryption of the underlying message. That upon decryption will get the message. So why this works? So basically these homomorphic fully homomorphic encryption schemes, so they have every ciphertext has what is called a noise component. You have the message, okay, and then by adding noise, it is kind of encrypted, and that noise doubles upon addition and it squares upon multiplication. So that's why it kind of supports many. So and if the noise hits some certain threshold, so and you decrypt it, you will not get the decryption will be erroneous. So this is a property. So really, the technical aspect. So ciphertext has a noise component that doubles, means there's a 1 bit increase in noise with every addition, and the bit length of the noise doubles upon multiplication. So this, if it hits a certain threshold, then you can no longer decrypt. Okay. So then if you apply this bootstrapping operation, so this will reduce the noise. The resulting cipher, so you still get the ciphertext of the underlying message, but then it will have less noise. So these are all some technical aspects which I will not get into detail. So I just wanted to introduce all these things. So in this talk, we'll just be worried about the application of this homomorphic encryption schemes. Okay. So there are already, like in past 10 years, so many works. So there are some 3 classes of the schemes, but I'll just not get into details. So whatever I'll speak on, they are based on the 2nd generation schemes. Yeah. I will not get into the details of these things. Okay. So there's a lot of efficiency improvement since the very original proposal of Gen 3. So initially it took, even the key generation took about 2 hours. So. And even the public key size was 1 giga, 2 giga, bits in length. So that was, or it's bytes. I'm not sure about that. Yeah. So basically, it's like a billion times slowdown, on your operations. So you could not even think of implementing even a very simple functions, homomorphically. But then now in 10 years, it's been a lot better. So it's all brought down to few megabytes. And as I mentioned, so typical computation, it would take, it's like a million times slower than what you perform on the plain text data. But there are some applications, mainly the low depth, circuits, they are pretty practical, So people at Microsoft Research, they already have demonstrated how you can do genome sequencing, or not the full genome sequencing, at least some primitive operations like Hamming distance computation, edit distance. So this you can all, in a realistic time, you can compute all those, So it holds a lot of promise, but then again, because it's so slow, there's a lot of scope for research. Or keep on working until someone shows that it's impossible, But in theory, even the Gen 3 scheme, the very original scheme, it runs in polynomial time, But it's just that the constants and the degree is so large that it is, kind of out of it's not feasible in practice. So though FHE schemes, they hold a lot of promise, so still encrypting your entire Gmail database and doing search on the encrypted data, it's still kind of, it's not feasible as of now. But looking at the improvements over the past decade, possibly, maybe another decade or a decade and 2 decades, who knows, it could be feasible. So what is the, so a realistic goal is to obtain, somewhat homomorphic encryption schemes. So what is somewhat homomorphic encryption scheme? It can evaluate functions of limited multiplicative depth, okay? So, and there are already kind of, sufficiently many applications, for those, somewhat homomorphic encryption schemes. So I went about, these things. Why the multiplicative depth matters? Because the noise, squares upon multiplication. So, and we need to contain noise up to certain level so that the decryption will be valid. So I went through all those things. Okay. So if we look at the applications, so what we should, typically study. First, we should understand the encoding data types. So here in this talk, we will see how to perform fixed point arithmetic in using somewhat homomorphic encryption schemes. Okay. And of course, first if we have a target application, so it will have its own data types, right? And then we should encode those data so that in the plain text space native for the somewhat homomorphic encryption scheme. Okay. Okay, I will get through that. Okay, so because when you use, for example, the Rsa encryption scheme, it should have your data should be encoded as an integer between say 0 and some number n minus 1. Okay, so that's what I mean by encoding data types. So you should encode the data from the application into the native plain text space of the homomorphic encryption scheme, and then of course derive bounds on the parameters so that so how to generate the key and what length they should be so that you can properly evaluate the function. Okay. So as I mentioned, the target application is how to emulate fixed point arithmetic using this somewhat homomorphic encryption schemes. And then why, so because the native plain text space consists of polynomials with integer coefficients. Okay. So this is a fancy math notation just to tell that the plain text space is the set of integers of bounded degree and the coefficients come from a bounded range. Okay, so this is a polynomial. So okay, so this C of m, it's a polynomial of some degree. Say for example, it could be of the form x power n plus 1. The moment you multiply when you add 2 polynomials, the degree is not going to increase. But when you multiply 2 polynomials, of course, the degree is going to increase. The moment the degree becomes equal to or exceeds x power n, then you need to divide with that polynomial. Okay. So, and then for the coefficients, they are all between the integers 0 to p minus 1. Okay. The moment the sum exceeds p, then there will be a wraparound. So formally what we do is the quotient, this all arithmetic modulo some p could be a prime number, and when you multiply, if the degree exceeds, so then you need to take the quotient. Okay. So now now the problem here is, suppose I want to say why we want to choose this plain text space like this is it's a design constraint. That's how the schemes are designed, for some security reason. Okay, we have to do this. And for example, let me give you a very simple example. Suppose you want to perform addition 7 plus 2, but I say that you can only do modular addition. What is a modular addition? You need to add 2 numbers and I will give you a modulus, and you should take remainder upon division by that number. Okay, suppose you want to perform 7 plus 2 modulo n. Okay, so then what is the minimum value you need to choose for n so that you will get the intended result, 9. So it should be, your n should be 10, right? So is it clear, the modular arithmetic? Probably you know that. Suppose I choose the modulus to be small, which is 5. So then 7 plus 2 modulo 5, which is nothing but the remainder upon division by 5, will be 4. But you cannot simulate integer arithmetic this way. Of course, you would simulate the modular 5 arithmetic, in a straightforward fashion, but in order to simulate the integer arithmetic, you need to choose n to be sufficiently large. So here, at least it should be bigger than the maximum possible result. Here it's 9, so your modulus should be 10. Okay, because here the degree, so here we encode any data as an integer polynomial, right? The moment you are performing operations, okay, so you want to multiply two real numbers, you encode it as integer polynomials, multiply. But if the degree exceeds 2 power whatever x power n or n, the degree exceeds n, then you will wrap around, right? This is what we want to avoid. Okay, so that's why the polynomial, the polynomial phi and the coefficient modulus should be large enough. The problem is the moment it becomes large enough, then your scheme should be will become slower. So in this work we see how to emulate this fixed point arithmetic and how to derive parameters for this. So that's all we do. So we are not really constructing an encryption scheme, but a new homomorphic encryption scheme. It's just that we are studying the existing scheme, and we are just looking at from the application point of view of performing fixed point arithmetic. But what is really interesting is, so the takeaway, before I get into details, so is the way you encode can have dramatic effect on the performance. So you can just, by tweaking the encoding scheme, not really constructing new homomorphic encryption scheme, you can have like orders of magnitude improvement. So this is not the case for the plain text data, right? Suppose you represent your data plain text, I mean on a processor using binary or decimal. Of course, it will be like a few factors slower, or there will be a difference in performance. But in the case of homomorphic encryption scheme, you can have orders of magnitude. Okay, so this is the takeaway. So from the top. Okay, so as I mentioned, we need to determine the plain text. So the plain text, the coefficient modulus and the polynomial modulus, right? Just deriving bounds for it. So I'll just quickly run over the at a very high level, run over the details. So first we looked at how to encode integers. So one way is just encode the integer as the constant of the polynomial. Okay, easy. But what is the problem? The moment you do many operations, so then that number is going to blow up, right? The moment again then you need to choose a large modulus and the scheme will become slower. That's bad. So what we instead we looked at what is called a balanced base B encoding. So here, so you need to encode an integer as a polynomial. Just write it out in some base B. Okay, and instead of that, so basically if I use the base B expansion and I write say some number and as say whatever, so alpha 1 or okay, alpha 1 b or alpha 0 b naught, alpha 1 b power 1, so on. So then I just encode it as the polynomial alpha naught plus alpha 1x, so on. Okay, and how to decode? So given this polynomial, I just need to plug x equal to 3, right? So, and when we did some experiments, it turned out that b equal to 3 is better, because you will start with small coefficients, and in this base 3 expansion, we will not use the coefficients digits 0, 1, 2. Instead, we will start with -1, 0, 1. This is possible. So you can even allow negative digits in the base P expansion. So what is the idea is, so the moment you start with small coefficients, means coefficients of small magnitude, and at the end of the result, it will be smaller. So that's what we experimentally observed, and yeah, so we go for this. So that is integer. For example, in the case of 19, in the balanced base 3 encoding, you represent 19 as x square minus x cube minus x square minus x minus 1. So the moment you plug x equal to 3, you will get back 19. Okay. And okay, and then of course, and we also we should remember that we need to derive bounds on the parameters, right? So given some function, how to derive bounds on that. So that is the next thing what we are going to see. So that is integers. Integers are encoded, but then how to encode fixed point numbers? It's so very standard ways. So represent, say we want to represent 19. So then say suppose you want to represent 1.9. It is just 19 into 10 power minus 1, right? So basically you are using the integer encoding, but you just need to obtain this exponent so that you can scale down the result. Okay, that is one natural representation. Okay, so if you have, say, some integer digits and fractional digits, you just scale it in such a way that, so suppose if you use the base 3 encoding, then you just represented the integer in the balanced base 3 and just keep track of the exponent. Okay, as easy as that. So coming back to the same example, if you want to encode 19 by 3 in balanced base 3, so it is just encoding 19 and keeping track of 1. Means you need to multiply by 3 inverse after you decode. As easy as that. Okay. And the only problem here is we need to keep track of the exponent in the clear, and so this will not achieve what I mentioned as circuit privacy. So you can kind of know what is the multiplicative depth of your circuit. But if you are evaluating a publicly known function, it's not a problem. Okay, yeah. So if we use this representation, so then we need to remember, we always need to achieve bounds on the maximum bounds on the plaintext modulus and the degree of the polynomial modulus. So, but analysis in the case of this, let's call this scaled integer encoding, it's the same as the integer encoding. Okay, so this is the problem what we will see. If we have a circuit, if you have many inputs, how to arrive at the bound? The max, that is, the bound is the size of the max coefficient, of the resulting output. And then your parameter should be bigger than that. Okay. And the people from Microsoft Research, they propose another very clever encoding scheme. So where so basically, of course, so suppose we are given an integer polynomial, on a fixed point number, and it has, say, y plus as its integral digits and y minus as the fractional digits. You can always represent this by this polynomial, right, which has negative powers also. The moment you plug in x equal to b or x equal to 3 in our case, then you will get back the value. But then using the modular property, because of the fact, so what modulo x power n plus 1 means is, whenever you get x power n plus 1, then it's equal to 0. Means x power n is minus 1. Okay, so that means even if you multiply, so if you change the sign and multiply by x power n, you will get back 1. So 1 is basically you can represent as, so here plus 1 into something, right? That 1 itself can be represented as minus x power n, because that's equal to 1, right? But then what is the advantage is, now all the exponents will become non-negative. So means the fractional digits are encoded in the top order coefficients. Okay, so decryption is very similar. So let's go back to the same example, x 6.33, which is 19 by 3. If you use the base 3 encoding, so then earlier we had to shift it by 3, right, into multiply by 3. You would have got x cube minus x minus 1, but then you will get it minus x power 7. So it's just the fractional digits are encoded in the leading digits. Okay, but the only problem, of course, now you need not explicitly keep track of the exponents. That's the one very good aspect of it. But then the problem here is, the moment you are starting with high degree polynomials, so then there is a chance that you will end up with much bigger numbers, and you need to choose much larger parameters, and then the whole thing is going to be slower. But our first result here is, so we saw two encodings, right? One, the scale integer encoding, fraction encoding. We show that as far as the size of the growth of the coefficients are concerned, they are identical. So basically, in a very technical terms, so we represent and we come up with an isomorphism between these two rings. I'll just not get into details, just to give you intuition. So here, this was the representation of 19 by 3 in the scaled integer encoding, and then this was in the fractional encoding, right? So now, how do you go from one conversion to another? Just by multiplying. If you multiply by minus x power 7 and go modulo x power 8 plus 1, then you will get back. So means coefficients, the signs might be different, but as far as the magnitude of the coefficients are concerned, it's the same, right? So the infinity norm, or formally means the magnitude of the largest coefficient, is the same. So though it encodes in the fractional encoding encodes in the leading coefficients, though there's a possibility of quicker growth, it does not. So as far as the analysis is concerned, we can just do the integer encoding. So represent all your fractional inputs as fixed point inputs as an integer and then do the encoding. So this solves the problem, So that's first technical result, and then we give bounds on all this, okay? So actually, it turns out to be, bit tricky. For example, it's quite difficult to give the bounds, So the study essentially has reduced to the problem of how the size of the polynomial grows, So if we take the case of expansion of x plus 1 power n, even determining the max coefficient to a high degree of precision is very difficult, And if we use analytic techniques, then we get all the approximation. For example, if you want to compute factorial, we have Stirling approximation, right? So because we have analytic tools, so that computing the approximations of those numbers becomes easy. But computing in exact is difficult. So here also, so we have some circuit represented as an arithmetic circuit, okay? And now all the inputs are encoded as polynomials. So and as they pass through the gates, the polynomials get added up or multiplied, right? And the coefficients, they increase, and coming up with the exact bound is difficult. So what we give is a procedure to do it. We go gate wise and then do all those bounds, and then so this will be helpful for practitioner. That's our hope. So finally, I think I should mention that we know the binomial expansion very well, right? 1 plus x power n. So now the next question is, it's a degree d polynomial, okay? So 1 plus x square, so on up to x power d. So why we took of this form? Because this represents a worst case input, right? In the worst case, all the coefficients will be 1, and then you encode, means, because remember, in the base 3, the balanced base 3 encoding, you start with -1, 0, 1. The worst case all being 1, right? So that's why all the coefficients are 1. And to the power e, you need to determine the max coefficient. It turns out that this problem was not like studied until recently. So Mattner and Roos in some statistics, it's in, I think, statistics and probability letters. So we had to dig it up, and by chance we found out, and they give very tight bounds, So it roughly grows as d plus 1 power e as one expects, but then, so this is a very tight formula. So binomial thing is expansion is so well known. The moment it gets generalized, then it's it becomes difficult. So I mean, I could not even understand the proofs. Just we used just the results of this. Okay. Yeah. So and then for a regular circuit, we can give a closed bounds. Okay. So this is where we choose the parameters. Okay. And then it turns out that suppose you have a regular circuit. What is a regular circuit? You have a layer of addition gates and then a layer of multiplication gates. So we have a alternating layer of addition and multiplication gates. So even if the inputs are 20-bit integers, suppose you have a multiplicative depth of 5, means you have 5 layers of multiplication, and in between each layer of multiplication you have a layer of addition gates. Suppose there are just 5 addition gates, So interestingly, the number becomes the max size of the output coefficient will be 424 bits. So just 20-bit input, very simple circuit, then it becomes 424 bits, and it's already like it's huge, right? And we need to choose the parameters for the worst case, and our computations become slow. So let me quickly go to the application. So probably as I mentioned in the beginning very briefly, so all these satellite operators, they use this shared infrastructure. For example, a satellite payload is owned by users, and ground stations they are owned by a third party, and of course data processing facility is owned by some other party. Okay, so here we have the satellites, then we have the ground stations. They are all owned by different parties. So now, so if satellite some raw data, so then it's some processing, basic processing is done, and then it's distributed to the respective users. Okay, of course the need for privacy will arise, right? So we can ask the satellite to just encrypt the data and send it to us. Okay, so that the privacy is maintained. Again, the problem is the moment you encrypt, things become slow, right? So we look at a very basic image processing pipeline. So it seems something called synthetic aperture radar. SAR is a basic, it's a image processing algorithm commonly used in this satellite application. Sorry, I'm not expert on this, so I had to believe my colleague from Thales UK who gave us all these applications. So we considered a very basic image processing pipeline. namely, so it will involve computing discrete Fourier transform, a Hadamard product. Hadamard product is just a component-wise multiplication, not the usual matrix multiplication, and then the inverse DFT. So this is a very basic image processing pipeline. So how to perform it homomorphically? Okay. So and our inputs were actually complex numbers, So complex numbers, we encoded it as the real part and the imaginary part we encrypted in separate ciphertext. Okay. So as I mentioned, this Hadamard product is a component-wise multiplication. If the Hadamard product, if it is publicly known, then the whole operation becomes linear. The moment it becomes linear, then we can already use a linearly homomorphic encryption schemes. Okay, but then there is no need for fully homomorphic encryption schemes or somewhat homomorphic encryption schemes. So instead, what we did was we encrypted the coefficients, the components in the Hadamard matrix product, and this makes the whole thing non-linear. And then we have to use a somewhat homomorphic encryption scheme. Okay, so just to recollect, what is a discrete Fourier transform? So basically, it's just suppose you have a vector of complex numbers, say in an n tuple of complex numbers, and then we multiply with a matrix of powers of roots of unity. As simple as that. That's a discrete Fourier transform. Equivalently, you can represent that vector as a polynomial, say ax power I, and then you are evaluating all those at the primitive roots of unity. Okay, that's it. Yeah. Okay, and so of course once you have, because the roots of unity, it's all scalars, right? There's no need to encrypt them. Okay, so you can just view it as the plain text ciphertext multiplication. Okay, so matrix vector, we know how to do it in a naive way, right? It just needs n square depth 1, multiplicative depth 1, and n square multiplication. But there is a clever algorithm called the Fourier. Okay, so DFT. What is that? Fourier transform, right? The full DFT, the discrete Fourier transform. So that's a divide and conquer approach. So you don't need to do n square multiplications. Only n log n multiplications is enough. But then you need to recurse down, right, up to some depth. Okay. So and there's a trade-off. Why as I mentioned, in the case of homomorphic encryption scheme, the longer the depth, the slower it's going to be. Okay. So it's a trade-off. In the plain text case, probably we would have gone for the full discrete Fourier transform. Okay. So for the divide and conquer approach, because it will save on the number of multiplications, right? Depth is not a problem. But here in the case of homomorphic encryption, because depth means the longer depth means it's slower, so there's a trade-off. So we looked at various levels of trade-off, and then we came up with the bounds on those parameters. So this is what we did. Okay, and then so probably this is most interesting. Even to do this basic image processing on say a component on say 256 elements complex vector. Okay, initially it took 10 hours for this. Just a DFT on complex numbers of 256 complex numbers. It took 10 hours in the first work. That's very, very bad, right? Yeah. And good. So that's a good. So there's a homomorphic encryption library called HElib. There's HElib. HE stands for home. Oh no. There's a library for that. So it's implemented in C++. So it involves many other mathematical libraries. So there's a library to do this. And it's not really it's not like as finished as MATLAB. So it's still in the development phase. Some academics are maintaining this library. So it's only for it's best used for research purposes. So 10 hours. Okay. So and then in the next paper we could bring this time from 10 hours to 10 seconds. So 3 orders of magnitude improvement. The trick is very simple. Earlier what we did was so what is a Fourier transform? Basically multiplying a matrix of the roots of unity with the given vector, right? But then how do you encode the matrix of the roots of unity, powers of roots of unity? First, you should take a fixed point approximation to that, and then represent it as polynomials. Okay. So as far as choosing parameters are concerned, you are multiplying the encodings of the powers of roots of unity, and then multiplying with the encodings of our inputs, and there it will result in a polynomial, the polynomial, right? And we need to choose the parameters such that the maximum coefficient is contained within that. Okay. But here the fact that if we are working in the rings of the form, say x power 2 power n plus 1, means you are going modulo this polynomial. This means that x power 2 power n is already minus 1, right? And if you square, you can get x power 2 power n plus 1 equal to 1. So what it means is x is already a 2 power n plus first of unity, right? So x algebraically encodes some 2 power n plus first of unity. So now means all the other powers of x will already become some powers of this, right? So means you're, instead of having first taking a fixed point approximation and then encoding it as a non-monomial, here we just need to encode the whole thing as monomials. And because of this trick, okay, all the parameters, they come down dramatically. So here we say, for example, I mentioned that just to do a Fourier transform on 256 element vector. So for example, if we want to do the full FFT, it needed plain text, the modulus of 93 bits. Okay, the plain text coefficient modulus. Now we can just bring it down to 34 bits. And then if we look at the timings, okay, so previously what it took 34,000 seconds, which is approximately 10 hours. Now it just takes 9.4 seconds. So one trick, and then of course so one can claim that these tricks, like, you cannot apply it for any computation. At least for this one can do. If you want to evaluate DFT like applications, then we also looked at some other applications. To some extent, yes, you can but in general, if you want to do any general computation, then the base 3 encoding and all this new encoding, they all behave the same. So depending on the function what we want to evaluate, then we need to carefully choose and set the parameters. So, and this is a non-trivial task. You need to get to all the math and then do it. So yeah, I think I'll just conclude. Yeah, I know. I'm sorry. It's technical, but I cannot avoid that.
What kind of operations frequently perform? What's the most complex operation?
This is the like homomorphic image processing. That is the
In terms of the arithmetic involved, what kind of underlying arithmetic? Even for image processing, there's some kind of addition, multiplication.
Oh yeah, it's a Fourier transform, inverse Fourier transform. This is the most complex thing we can do. So you probably are aware, right? So we are doing a project with Sonata software. So I'm me and my student Shyamurthy, we are looking into how to apply this homomorphic encryption in the case of securing the privacy of users and drivers data in the travel setting. Like for example, Uber. So currently we know the user knows the driver's location, and of course Uber knows everything. And there are already numerous data breach instances that has happened. Uber, and they are actually compelled to use some techniques to anonymize the data and all, so that users' privacy is maintained. So we are trying to look into use of homomorphic encryption. So of course, because it's too slow, there are already some recent work that showed this is feasible, but that still is in the research phase. So we want to look into it and make it more practical. So that's because still that's a work in progress. I did not get into the details of that.
When you mentioned this billion times slowdown, is it again, when there are bounds in terms of what those computations?
Oh yeah. A typical function.
Doing arbitrary.
Yeah, for arbitrary, yes. So ultimately, what really matters is the multiplicative depth of the circuit. If it is small, you can do, for example, just computing Euclidean distance is super quick. because it's just one subtraction and one squaring, right? Squaring is just one multiplication.
Does that mean like for a long time you really expect to take advantage of the specific nature of
Yes, yes,
some
yeah.
of this feasible enough scheme?
Yes, yeah. Actually, that's what we have been doing, For now, and if someone comes up with a very clever construction of homomorphic encryption scheme, then that's going to solve all the problems at once. Yeah, so I think, yeah. Thank you.